nuclear reactors are found in many industrialized countries throughout the world. They can produce large amounts of electricity from a small amount of fuel. In fact, a single pellet of uranium fuel will produce as much electricity as 1 ton of coal. The secret to this almost magical creation of huge amounts of energy lies in a process called nuclear fission. When a uranium-235 nucleus is struck by a slow-moving neutron, the nucleus undergoes fission to produce lighter elements. 2 or 3 neutrons are also released. If these neutrons are slowed down, they may cause another uranium-235 nucleus to fission. In the core of a nuclear reactor, enough slow neutrons, under the right conditions, will produce a self-sustaining chain reaction. When each fission takes place, some mass disappears. This missing mass is converted into the kinetic energy of the fission products. In a nuclear reactor, this kinetic energy is used to heat water, which is carried outside the reactor core, where it is converted into steam. The steam turns a turbine, which is connected to a generator, which produces electricity. The electricity, conducted down high voltage lines, is the useful product tapped by industry and the homeowner. But the reactor produces a not so useful form of energy, which presents us all with a headache. The amount of the fuel that is placed in a reactor and the general appearance of the fuel at a glance seems hardly changed when it's removed months later. But this spent fuel is highly radioactive. It must be handled by remote control, and it must be carefully stored for hundreds of years to prevent contamination of the environment. Compared to the high levels of radiation from the used fuel, unused fuel emits fairly low levels of radiation. Why is there such a difference? Let's examine the unused fuel rod first. To make things simple, we will assume that the fuel consists of pure uranium. Since the vast majority of the atoms are the isotope U-238 and only a few U-235, we will consider only the uranium-238 at this stage. It is radioactive and has a half-life of 4.5 billion years. When it decays, it emits an alpha particle and a gamma photon to become thorium-234. But things don't end here. We need to go through 12 more steps of this decay series before we get to a non-radioactive element. Don't try to remember all the names. Do notice the different half-lives. Also notice that by the time we get to the end, 3 forms of nuclear radiation, namely alpha, beta, and gamma, have been emitted. Finally, we arrive at a substance that isn't radioactive, lead-206. In the sample as a whole, all the various steps in the decay sequence are present at any one time. As a result, the sample appears to be radiating alpha, beta, and gamma radiation. The very long half-life of U-238 means that the overall rate of decay in the unused fuel will be relatively slow compared to the very strong radiation of the used fuel. Now, let's begin the fission process in the reactor core. The actual fuel is uranium-235, which only makes up a small portion of the total material in a fuel bundle. U-235 undergoes fission when struck by a slow neutron. This releases energy and also results in the production of lighter elements. There are many possible combinations of fission products of this uranium-235 fission. Let's examine strontium-95 and xenon-139, just one possible pair of products. Strontium-95 is radioactive. It decays in a series of 4 steps to form molybdenum-95, which is stable. The other fission product, xenon-139, is also radioactive. It decays in a series of 3 steps to form lanthanum-139, which is also stable. So, the fuel in the reactor core begins with the natural decay series of U-238, which produces only a little radiation. But as fission begins, a variety of fission products with very short half-lives are formed. These decay rapidly, and a great deal more radiation is produced. And that's not all that's going on inside the fuel. Even though a U-238 nucleus will not fission when struck by a slow neutron, it may, however, absorb a neutron to become uranium-239. Another decay sequence begins to produce plutonium-239. To make things even more complicated, plutonium-239 will undergo fission if struck by a slow neutron to produce still more radioactive products, which in turn decay. This fissioning of plutonium-239 actually accounts for 30% of the energy produced in the reactor, while producing a whole set of more complicated decay sequences which add to the radiation from the fuel. When the fuel is removed from the reactor, the fission process stops, but not the decay chains. The high level of radiation coming from the spent fuel is caused by the many radioactive elements still present in the fuel rod. Since many of these have a short half-life, the radiation from the fuel will drop dramatically in minutes, hours, and days after it has been removed from a reactor. Because many radioactive isotopes in the spent fuel are present in large concentrations and have long half-lives, the spent fuel poses a danger to the environment for many thousands of years. Researchers are now looking for ways of safely storing this waste, for example, in caverns deep within stable rock formations. Is it possible to harness nuclear energy, or any energy source for that matter, without risks to ourselves or our environment? Some are now pinning their hopes on nuclear fusion, the process in which 2 nuclei fuse together to form a heavier one. But nuclear fusion will no doubt have its share of dangers, the same way hydropower has broken dams, the way coal-burning plants produce acid rain, and the way nuclear reactors produce radioactive byproducts. As with so many of the discoveries in science, the secret of nature, unlocked by Becquerel, can both harm us and help us.